All right, so let's understand the random variable. Random variable is foundation for statistics. It's an idea that helps analyze data mathematically. So we need to understand that concept. A random variable is basically a rule that assigns a number to each outcome of an experiment. So each outcome of an experiment is going to be related to a number. How you define that number depends on what kind of analysis you're doing. So there are all kinds of different ways of assigning a number. Um, in in real life problems, real life situation, every exam paper has an associated number, which is a grade. And for every student, we can assign a number, which will be either age or height or, things like that. So a variety of different numbers can be assigned. And what number you want to assign um, to the outcomes of an experiment depends on what analysis you are interested in. So the problem will normally define what your random variable is. You don't have to define it. And then based on that definition, it'll ask you questions. So here's an example. And we name the random variables as X and Y. So random variable represents more like a function in math. If you understood function, the same idea. It will associate a number to each outcome. So here's an example. Toss two coins. That means outcomes are going to be two letters, HH, HT, TH, TT, and random variable is defined to be number of heads. So how many heads are there in each outcome? That number will be the value of the random variable. So here's the list that shows the values of the random variable. So outcome I'm writing all possible outcomes here and corresponding value for the random variable. So since the random variable represents number of heads, then the outcome is HH, value of X is 2. For the HT, it's 1. For the TH, also 1. For the TT, it's 0. So random variable can take the value 0. You can take the negative numbers too, depending on the definition. So that's an example. Let's do another example. Toss two 4-headed dice. And so each die has 4 sides. And so whatever shows at the bottom, when it comes to 4-sided dice, 4-side means it's a tetrahedron, not a rectangular shaped or not a cube shaped dice. So 4-side means it's a tetrahedron. And so the side that falls at the bottom is the one you read as your outcome. Anyway, the random variable is defined to be, random variable has to associate a number to each outcome. That's all it is. So it can be defined in all different ways. So this one is defined as sum of the faces, the total of the two faces. That's your value of the random variable. The outcome of tossing two 4-sided die, I have written all of them. 1, 1, 1, 2, 1, 3. These are all of the outcomes. And here are the values. If the outcome is 1 on the first die, 1 on the second, then the sum is 2. It's as simple as that. So as you can see, the value 3 occurs more than once. There's one, there's another one here. So more than one time, each value can occur. Value 4 occurs here and here and here 3 times. So each value can occur more than once. The number of times each value occurs is called frequency of that value. So we'll discuss that on the next page. Here we'll understand the range of random variable first. The range of a random variable is set of all the possible values it takes. So you have to collect all the values random variable takes and put it in a set. And that set is the range of X. So going back to this example 1, X is defined as number of heads, and here are the values it takes. So when you write the range, you just list each value once. So therefore 0, 1, 2 are the values. 0, 1, 2 are the values in the range of X. Okay, what are the values in the range of Y? Anybody?
2, 3, 4, 5, 6, 7, 8.
Right, 2, 3, 4, 5, 6, 7, 8. Very good. So here is the range of Y. All right, exercise 1. In the experiment of tossing a die, random variable X is defined to be outcome itself. You can call the outcome itself as your value of the random variable. So I'm tossing a die. The outcome, whatever the outcome is, that is the value of the random variable. Then can you write the range of X? Or tell me, go ahead and tell me the range of X. You're tossing a regular die. The
1
die.
and 2?
So go ahead. I'm sorry.
Is it 1 and 2?
Why just 1 and 2? It's a die with 6
Oh,
pieces.
1, 2, 3, 4, 5, 6.
Right. 1, 2, 3, 4, 5, 6. That's it. Okay. Second exercise says a jar contains 4 red marbles and 3 green marbles. From this jar, 4 marbles are taken. Random variable X represents count of red marbles in the selection. So I'm taking 4 marbles, and the count of red marbles in the selection is going to be my random variable, the value of the random variable. Okay, then what is the range of this X?
Isn't it 1, 2, 3, and 4?
Yes. Why not 0? Yeah, you're right, but just explain why 0 is not one of them.
Because 0 would then include it being a non-existent red marble, right?
The 0, yes, no, 0 means no red marbles. Now that's not possible. Why? Because there are only 3 green marbles and we are taking 4. So there must be at least 1 green, right? So there, in other words, 0 red is not possible. There must be at least 1 red, right? You have to think about that. Think about the details. Okay, 1, 2, 3, 4 is correct, but can 0 be there in the list? No, because we are taking 4 marbles and there are only 3 green marbles, so we cannot have 4 green marbles. So there must be at least 1 red. So therefore, 0 is not a possible value. 1, 2, 3, 4 is correct. Ask question if you're not following me. All right, so far we understood what a random variable is. And now we're going to learn the classifications of random variables. A random variable can be classified into 3 kinds: finite discrete, infinite discrete, continuous. And you have to be able to identify a random variable as one of these. And so let me explain what each one means. A finite discrete random variable will take values that are finitely many. In other words, you have to look at the range of all the values. If the range has only finite number of values, then it is finite discrete. So let's go to one example. Look at the range of X, 0, 1, 2 are the only values. That's finite discrete. Range of Y is also finitely many, finite discrete. So if it is finitely many, then it is finite discrete. But infinite discrete means the values are infinitely many, but discrete means you can actually list them. The discrete means you can list them, you can put them in an order. Even though they're infinitely many, you'll be able to tell, okay, it's like a series, 2, 4, 6, 8, dot, dot, dot. It goes infinitely many, but there's a pattern, so I can write it down. So infinite discrete means infinite number of data, infinite number of values for the random variable, but you're able to write them in an order. here's a example, a simple example to illustrate infinite discrete. Toss a die until it shows 4. So I had to keep tossing until it shows a 4. Then how many times do I have to toss? That's my random variable. The random variable represents number of tosses I had to make until I get 4. So that number of tosses can be 1. In one toss, I can get a 4. Or it can be 2, 3, but it can go on. We cannot tell exactly how many tosses it's going to take, right? It's going to go infinitely many. Can I say in for 10 tosses, I'll get a 4? I can't tell that, right? So that means the list is going to go on infinitely many. So this list is going to be, the values of this random variable will be 1, 2, 3, 4, 5, 6, all the way to infinity, but I'm able to list them. So when you can list them, it's infinite discrete. So discrete basically means, you can put them in order, you can arrange them. The next one is continuous. So finite discrete, if it is finite, then it is finite discrete. If it is infinite, but you can arrange, then infinite discrete. Continuous means it's infinite and you cannot arrange them. It's like all the numbers between 1 and 2. If the value of the random variable is all the numbers between 1 and 2, what is the first number after 1? Can you tell? Number, it's not integer. It's any fractional number. After 1, if you say 1.1, I can say, no, 1.01 is smaller than that. And if you say 1.001 is the number, I can say 1.0001 is smaller than that. You can't even write down the very first number between 1 and 2. So that's when it's continuous. All the numbers between 1 and 2 is a continuous chain of numbers, infinitely many, even though they are all between 1 and 2. There are infinitely many numbers, and you cannot even list them. So I have an example of, so this continuous random variables are uncommon. They don't occur too many times, but you have to know what they are, and in statistics you have to sometimes deal with them.
So for continuous
uh,
variables, decimals are basically included, right?
yes, for all of them, even for the discrete ones, infinite discrete, the numbers can be decimal, but if you can write them in an order, then they are discrete. So here, the continuous case, the numbers, it can be in a small range, but they can be infinitely many, and you cannot even write down what they are in an order. You cannot arrange them in any order. So let's look at a simple example. Now, like I said, the continuous random variables are uncommon, but so the example is going to be kind of uncommon. So here's my example. Turn on a flashlight and leave it on until it dies. And the random variable Z represents length of time it takes to die. Okay, that length of time could be 0.1 minute or 1900 minutes. We don't know, right? It's and it can be a fractional number. So we cannot even tell a range between what and what, So there is no listing of these values. They are infinitely many and they are continuous. In other words, you cannot write them down in any order. All right, so those are the classifications, and you have to be able to classify a random variable as one of these. Exercise 3, classify the following random variables. The first one is from a box of clearance items in a hardware store. You're taking one item. A random variable X represents price of the item. So from a clearance item box, you take one item and read the price. And that price is your value of the random variable. The experiment is taking one item from the clearance box. Okay, so is this going to be, the numbers are prices of the item. So what is the classification of this random variable?
Is continuous.
Okay, anybody else?
I think infinite discrete.
Infinite discrete, okay. Any other answer? It's neither infinite discrete nor continuous. It is finite discrete. Why? Even though the numbers are fractional, like $2.50, $3.40, things like that, how many items are in the box? Finitely many, right? You can't put infinitely many items in a box. So since the items are finitely many, the numbers can be arranged in order, right? If I give you 5 numbers, no matter how big or how small they are, you can arrange them. If it is finitely many, you can always arrange. Only when it is infinitely many, then you have to think about, can we arrange them, or are they numbers we can arrange, or are they numbers we cannot arrange? You ask those questions only if they're infinitely many. If they're finitely many, you don't need to ask those questions. If any finitely many numbers can be arranged. Okay, it's okay to answer it wrong. Go ahead and answer the question. That way we generate a discussion in which you learn the right way. Okay, repeatedly toss 3 coins until all of them show head. So until all of them show head, I'm going to have to repeatedly toss them. Random variable y represents number of tosses. Okay, what's the classification?
Is this one infinite discrete?
Infinite discrete is right, because the number of tosses is going to be a whole number. 1, 2, 3, 4, infinitely many, but they're whole numbers, so we can arrange them. So therefore, it is infinite discrete. Okay, toss a die repeatedly until it shows 4. Write the range of values of x. Is this finite, discrete? Okay, that's a fairly easy question. Go ahead, tell me, what are the values? What is the range? I'm tossing the die.
1, 2, 3, 4, 5, 6.
Okay. One, I'm not trying to write down. Okay. So it'll be 1, 2, 3, 4. But it's not going to stop at 6, right? It's going to be ... It's okay to write with the ... It's going to be infinitely many, right? Because we don't know how many tosses it takes to get the 4. So what is the classification?
Infinite
Infinite
discrete.
discrete.
Infinite discrete. Very good. Okay. Next question says, random variable x represents the length of time an athlete ran in a 10-mile marathon. Length of time an athlete took to run a 10-mile marathon before giving up. So what kind of, so what's the classification of this random variable?
Could it be continuous?
Yes, that's right. It's continuous because, maybe the time it's 10-mile marathon, so that maybe the time has a limit, but every number between 0 and that largest number can be a possible number, right? Every number is a possible number for the time it takes for an athlete to finish that or give up. So it is continuous. All right, moving on to frequency distribution. So in statistics, you basically write your problem as a problem involving random variable. Whatever you're dealing with, whatever you're analyzing, you can define a random variable that represents it. So you define the random variable, and then you write down all the values your random variable takes, and then you write down the frequency distribution. And I'm going to explain the frequency distribution. You just list all the values random variable takes and how often it takes, or how many times each value repeats in the range. If you look at the range, some values, not the range. I mean, if you actually look at all the values the random variable takes, some values will be repeating, and how many times they repeat, you write those frequencies. So the number of times each value repeats is called the frequency. And so you're going to have to list each value the random variable takes and the frequency of those values. So let's go back to the same example we did before. The random variable X in example 1, which is tossing two coins and looking at the random variable representing number of heads. Go back to that. Here, I'm tossing two coins, and random variable represents the value. The value of the random variable is number of heads. So here are the values of X. And if you look at these, the value 0 is repeating only once. The value 1 is repeating twice. In other words, two outcomes represent value 1. Only one outcome represents 0. So we say that the values of X are 0, 1, and 2. 0 has a frequency of 1. 1 has a frequency of what?
2.
2. And the value 2 has a frequency of
1.
1. So that's what your frequency distribution is. So here is the frequency distribution. Where is that? Right here. So here's the frequency distribution. So if they ask for the frequency distribution, you have to show this table. Values of X are 0, 1, and 2. Frequencies are 1, 2, and 1. For the 0, frequency is 1. For the 1, frequency is 2, and so on. All right, so let's do another example. The tossing four-sided dice. That was example 2 being repeated here. If you toss four-sided die, and if the random variable represents some of the phases, then I'm listing all those values, all those outcomes and the values. The outcome 1, 1 gives you value 2 for the random variable. The outcome 1, 2, and 2, 1, both of them give you value 3 for the random variable. And outcomes 1, 3, 2, 2, and 3, 1. 3 outcomes give you the value 4 for the random variable. So therefore, frequency of 4 is 3. 3 outcomes give you that value. Frequency of 3 is 2. So you can see different, each outcome has different frequency. So this first 2 columns represent the frequency distribution. I'm showing the third column so that you can understand which outcomes represent these values. Those third column shows all the outcomes of this experiment, all the outcomes. And first 2 columns tell you the frequency distribution of this random variable. So this 2-column report you see here is called frequency distribution of the random variable. And if you add up the frequencies, that should be equal to sum of the count of all the outcomes, obviously. There are 2 outcomes that give you the value 3, and that's why the frequency is 2. So the frequency is 2 means there are 2 outcomes in the sample space that will give you value 3 for the random variable. And 3 outcomes give you value 4 for the random variable. So if you count all of these, that's 16. So therefore, these frequencies should add up to 16. because you have to account for every outcome. And so clearly the frequencies must add up to the count of the sample space. So you need to remember that. The frequencies must add up to the count of sample space, otherwise frequency list is wrong. Now, once you write down the frequency distribution table, you can write down the probability distribution table. Probability distribution table will show probability for each outcome. In other words, let's look at an example. If I ask you in this experiment in example 7, I'm tossing 2 dice, 2 4-sided dice, and random variable y represents 3. And I ask you to find probability for the random variable y to get value 3. And we write that in statistics this way: probability for y to be equal to 3. That means the random variable y to take the value 3 is what this means. Probability for random variable y to take the value 3. Okay, now look at the table. How many elements in the sample space will give you the value 3 for the random variable? They're here, right here, 2. So therefore, what is the probability for y to be equal to 3?
2/16.
2/16, exactly. Very good. So the same as this frequency divided by total frequency. See that? Okay, one more example. 5. Value of random variable to be 5. We write that as, so this is 2/16. Probability for y equal to 5. What is that?
Yes, they are.
4/16.
4/16. Did someone say a different number? If you did, I just want to know what it is and explain. Okay, doesn't matter. 4/16 is the number. And that's same as you can see, that 4 is the count of this, count of elements in the sample space that will make this event happen. The event is random variable equal to 5. That's the event. So the number of elements that in the sample space that make this event happen are 4. And that is the frequency. So in other words, what I'm trying to say is, once you have the frequency distribution, your probability distribution can be written in another column in the following way. You just divide the frequency of that particular value by the total frequency. So this divided by this frequency is your probability for the random variable to take the value 3 and so on. So divide each frequency by the total frequency. For this reason, the probability is sometimes referred to as relative frequency. Relative frequency means the ratio of the frequencies, ratio of frequency as opposed to total frequency. The probability is same as frequency divided by total frequency. So therefore, sometimes your web assigned question, if it tells you what is the relative frequency table, that's same as probability table. Okay, frequent probability distribution table. So that would be showing all the probabilities. So here is my example 8 is, again, the 4-sided dice. If I toss 2 4-sided dice and define the random variable y as sum of the faces, then my we already saw this frequency distribution in the previous page. And all you have to do is divide each number by the total frequency to get the probability numbers or relative frequency numbers. So this is 1/16. The probability for random variable y to take value 2 is 1/16. Random variable to take the value 3 is 2/16. The frequency divided by 16, and so on. So I have all the frequencies, probabilities here. Now there's a fact you need to understand here. All these frequencies add up to 16. And all those frequencies are the numerators here. So that means if I add up these numbers, the denominators are all 16s. So I will end up adding numerators, and these numerators would be adding up to 16. So can you see that? If I add these up, I'll get 16/16. Everybody see that? Okay. So the total probability is 1. That makes sense. We know that the sample space has a probability of 1. So if you account for all the outcomes in your distribution, then the probability distribution should add up to 1 if you have accounted for all possible outcomes. So that is a property of the probability distribution that you need to remember. So if a question says, is this a valid probability distribution table? Then your answer would depend on adding up the probabilities. You add up the probabilities and see if it is equal to 1. That's how you verify it's a valid distribution. If it is not 1, then it's invalid. Something is missing. Okay, probability, a given probability distribution is valid if and only if the probabilities add up to 1. Okay, this relative frequency I already explained. The probability distribution is also called relative frequency distribution. Okay, we already did this. Probability for y equal to 5 is 4/16 from the table. Now, if I ask you, what is the probability y less than or equal to 4? Let me explain that on the board. Probability for y less than or equal to 4. Sorry. I'm writing that in programming language. I just taught programming class, so I can't get over the habit. Probability for y less than or equal to 5 is, okay, if y to be less than or equal to 5 means y has to be equal to 1 or a 2 or a 3 or a 4, right? Or a 5. So that means what? Y less than or equal to 5 is same as this event. This is an event right now. Is same as getting y equal to 1 or y equal to 2 or y equal to 3. Those events, the union of those events equal to y less than or equal to 5. So if this event is the union of those events, then the probability of this event is the sum of the probabilities. Remember, probability of A union B is probability of A plus probability of B plus probability of C, D, whatever, minus the intersection of all of them. But there is no intersection in this case. Is there a common element that will give you y equal to 1, 2, and y equal to 3? No, y can be either 2 or 3, right? There is no element in the sample space that will give you 2 or 3. So there is nothing, no intersection. Y equal to 1 means the events that are in the event, the elements that are in the event y equal to 1 and elements in the event at y equal to 2 have nothing in common. There is no way you can get 1 and 2. Okay, so there's no intersection. So therefore, they are mutually exclusive events, and therefore the probabilities simply add up. Intersections are empty. So probability for y less than or equal to 5 is same as probability for, actually, I'm sorry, less than or equal to 4 is the question. Probability for y less than or equal to 4 is same as the probability for y equal to 1 plus probability of y equal to 2 plus probability of y equal to 3 plus y equal to 4. So probability for y equal to 2, no, y equal to 1 is not a possibility. Y cannot be 1, so sorry. So probability y equal to, for y equal to 2, y equal to 3, and y equal to 4. And that means these three numbers add up. That's how you find probability for y less than or equal to 4. And so that's what I'm explaining here. The union rule is what we are using to find that. And these events are mutually exclusive, so there's nothing in the intersections. So you add up these numbers to answer the question. Okay, exercise 6. In this last example we just did, can you find probability for random variable y to be between 4 and 6 inclusive? Go back, 4 and 6 inclusive. Anybody? Which number should I add?
1, 2, 3, 4, and 3.
Uh,
4, 5, 6.
4, 5, 6. I think you're looking at frequency. The value for the random value of the random variable y should be between 4 and 6. That means these, right? Okay. So probability for y equal to 4 is this. Probability for y equal to 5 is this. Y equal to 6 is this. So do you see that? We need to add up these numbers. Okay. Ari, Pasha, you got it?
Yes, Professor. Mm-hmm.
All right. So you need to find the probability. Now, don't look at the frequencies. It's the probability that's we are asking. It's a p. P, see the p, y less than or equal to 4. P stands for probability. Probability for y to be between 4 and 6. Okay. That is equal to sum of those three numbers. These three numbers. Okay. You're going to be answering questions like that in the homework. Just make sure you understand what's going on. It's not difficult. You can see that, right? You had to understand it though. All right, this question says 2 cards are drawn from the deck of 52 cards. The random variable X represents number of jacks. So I'm just taking 2 cards and my random variable represents number of jacks I have, okay, in my hand when I take 2 cards. All right, so let's see if we can write down our frequency distribution and all those. You can actually answer this question without writing everything as a list, but I'm going to take this opportunity to explain how to do that, how to write the list. Okay, so the random variable represents X represents a number of jacks. Okay, can you tell me what values X can take? Number of jacks?
1, 2,
1,
3,
2,
4.
3, 4, 5. And then it goes up to 13.
I'm only taking 2 cards. 2 cards. Okay. And how many jacks, the number of jacks is the question, right? Number of jacks is my random variable. I'm only taking 2 cards. So somebody said 2, yes, 2 is possible value. That both cards I took can be jacks.
4 and 4?
Why 4?
Because isn't there 4 jacks?
No, I'm only taking 2 cards. So do you realize that number of jacks I have in my hand has to be 2 or less?
Okay, so it's just 2.
Or
1.
Or
0.
0. I may have no jacks. I'm taking 2 out of the 52 cards, right? It may not be a jack. And I may have 1 jack or 2 jacks. That's it. 0, 1, 2. Those are the only values of the random variable. Okay, now let's take the frequencies. How many outcomes will give you 0? Only 1. No
1.
jack. Yes. How many outcomes will give you 1 jack?
2. Wouldn't it be 2 chances? Because the first one could be jack, and the second one could not. And then there's another chance that one could be jack and one couldn't.
Right, the first one jack or second one. The order doesn't matter here. So that means the first, second, we don't need to talk about. So one of them being jack is there are 2 cards drawn. One being jack means one outcome, jack and no jack. One jack and the other one is not a jack.
So the arrangements wouldn't matter.
No, problem doesn't, the value of the random variable represents, it doesn't represent the order. So the order doesn't matter. So therefore you can have one jack and the other one is not a jack. One, yeah, well, the order doesn't matter. Hold on. And you have to look at all the possible jacks. Different jacks are there. So you had to look at all the possible outcomes here. You're taking two cards. So those two cards, when they're both jacks, you have to look at the sample space and take all the outcomes that have two jacks. Understand what I mean? To count them. So that means if you take from 52 cards, if you take two cards, the sample space has, the count of sample space is 52, combination 52 comma 2, right? So among those two combinations of two, how many have how many have one jack and one not jack? You have to put all those counts in here. And how many have no jacks? You have to put all of those. So sorry, our numbers are not correct. We need to, so it's a little bit more than what it appears to be. You really have to look at all of the elements in the sample space and count, determine the count of how many have two jacks or how many have no jacks and how many have one jack. All those, they're much larger than you anticipated. So we don't need to go into all of that detail. We can just answer the question by doing this. Probability for x equal to 2 means what is the probability that two jacks are drawn, right? Okay, so we can answer that by saying there are, both of them have to be jack. So therefore, first of all, the number of elements in the sample space is going to be the same as the sum of the frequencies. Remember, sum of the frequencies equal to number of elements in the sample space, always. I explained that in the previous example right here. There are 16 elements in the sample space for this experiment, and that's why we got the 16 here. So number of elements in the sample space or the total frequency is same as number of elements in the sample space. So that's C52 in this case, C52 2. So we need to simplify that number. And then the event of elements in the event of x equal to 2. That means two jacks. Number of elements in the event of getting two jacks is same as the number of cards in the number of elements in the sample space that have exactly two jacks. Can somebody tell me what's the count of that? It's a combination of
4, 2.
4, 2, exactly. There are 4 jacks in the cards, 52 cards, and your 2 cards have to come out of those 4. So C42 is the count. So the probability for x equal to 2 is essentially same as the question of how many, if I take 2 cards from the 52 cards, what is the probability that both of them are jack? That kind of question you answered before. So the answer is same as C42 in the numerator, C52 2 in the denominator. Probability, this x equal to 2, this has a probability equal to same as this. This number is the probability that goes here, right here, for this number 2. So we don't need the frequencies, but we can go directly to the probability. We did that before. So that's the answer to that exercise. Going over to exercise 8, it says in example 8, what is the probability that y greater than 4? Going back to this here, what is the probability of y greater than 4? What number should be added up? Y greater than 4, not greater than or equal to.
Wouldn't it be 5, 6, 7, and 8? So
Yeah.
4 over 16 and 3 over 16, 2 over 16, and 1 over 16.
Right. Add up those numbers, the ones I have highlighted here. Very good. Probability for random variable to be greater than 4 means everything in this highlighted area. You need to add them up. So if you already have this probability distribution list, then you can just add those up. But probability distribution list for this problem, this Scott problem we just did, is difficult. It's very long list. We don't need to go into all of those, and you don't need to. We can answer whenever you can answer the question without making the table, you should do that. The table is not required to answer the question. Okay, now let's go to, let me explain something in this frequency distribution or probability distribution table. Probability for y greater than 4 is some of these. Probability for y less than or equal to 4 is some of these three, right? And so probability for y greater than 4 and probability for y less than or equal to 4 are complementary. They should add up to 1. Everybody see that? This is probability for y less than or equal to 4, the sum of those. Probability for y greater than or equal to 4 is sum of these. And both of those should add up to 1 because the total is 1. So always that's true for any kind of event. Y less than 4 and y greater than or equal to 4 are complementary. Probability of this and probability of this will be 1. That's true for any value of the random variable, not just 4. It will be true for 1, 2, or 3. For any value of the random variable, probability for y to be less than or equal to that and probability for y to be greater than that would add up to 1. And that's what I'm explaining here in this box. Okay, so here is a problem with the probability distribution. This gives you the probability distribution. In other words, so when they write the table, it's a standard notation for the table is this. What you write as xi represents the value of the random variable. So these numbers are the values of the random variable. So in some books, they will write capital X here in this as the column title here. Some books will write xi. The xi represents value of the random variable x. So just remember that notation. So these numbers are the values random variable x can take, all these, and these are the probabilities for those values to occur. First question is this a valid probability distribution? What do I need to do to answer that question?
Could you possibly add up all the probability of x to see if it equals to 1?
Right, exactly. You need to add up the probabilities and make sure they add up to 1. So let's go ahead and do that. 0.5, 6, 8, 9, 10. Yes, they do add up to 1. So therefore, the answer would be, yes, it is a valid distribution. And so it says justify the answer. That would be the probabilities add up to 1. That is your justification. Okay, what is the probability that x is less than 6? Anybody?
0.2 plus 0.3 plus 0.1.
Right, 0.6. That's right. That's equal to 0.6. Probability for x greater than or equal to 6 means we add up
0.4.
0.4. Add up these numbers. If anybody is not following, please stop and ask the question. Okay, probability for x less than 6 and probability x for x greater than or equal to 6 should be equal to what?
1.
1. We don't even need to manually add them. What is the probability for x to be between 4 and 8?
0.3 plus 0.1 plus 0.2 plus 0.1.
Right, these numbers have to be added up. Exactly. Very good. All right, so that means you understand the
I'm
distribution.
sorry.
Yeah.
For letter E, can you go over that one more time?
Probability for x to be between 4 and 8. So random variable x should be between 4 and 8 means it should be in this range, right?
Okay, so it's just 4 less than or equal to x and less than equal to 8 would just be in between 4 and 8.
Right. It means
Okay,
see
that's
this
the range.
this can be read as x greater than or equal to 4, right?
Okay,
And at the same time, x must be less than or equal to 8, which means it should be between 4 and 8.
okay, thank you.
Can you explain C again, Professor?
Part C, okay, x greater than or equal to 6. So that means 6 included, x greater than or equal to 6. So it can be 6, 8, or 9. 6, 8, or 9. The value 7 is not taken by this random variable. So random variable doesn't have to take every integer, right? So this random variable takes values 2, 4, 5, 6, 8, 9. Those are the values that this random variable takes. So what is the probability that x greater than or equal to 6 is the question. That'll be for the values x equal to 6, 7, 6, 8, and 9. You need to add up the probabilities, right?
Okay.
That would be 0.4. 0.2 plus 0.1 plus 0.1, which is 0.4. Okay, going over to the exercise 10. This one says, this is the probability distribution table given to you, and there are 2 probability numbers unknown. Okay, then first we need to find the value of A. So can anybody find it?
Would it be 0.2?
0.2 is correct. Okay, for anybody who doesn't see, let me explain. All of these must add up to 1. So since these 2 are both A's, they're equal. So 2A plus 0.6 equal to 1. By solving it, you can find A equal to 0.2. Okay. Since they should add up to 1, we can find A. Or you can simply, without writing any question, you can say, all right, these 3 numbers add up to 0.6, and therefore these 2 should add up to 0.4. So each one should be half of that, 0.2. This question says, find the probability that x greater than or equal to 0. The random variable is greater than or equal to 0. What is that?
0.6.
0.6. What is the probability random variable is less than 0?
0.4.
0.4, right. Okay, we already did that. Exercise 11 says 3 coins are tossed at the same time. Random variable x represents the number of heads that show up. Write the range of values of x, and and then you have to determine whether it's finite or infinite or continuous. Okay, so 3 coins are tossed at the same time. X represents number of heads showing up. All right, so let's see. I'm going to make a table showing the random variable x represents number of heads. Okay, so x is my first column, and I'm going to write the outcomes on this third column. number of heads can be equal to 0. Agree with that?
Yeah.
Yes.
And so that would be, we are tossing a coin 3 times. So what outcome will give you x equal to 0?
Tails, tails, tails.
Right, tail, tail, tail. And random variable can be equal to 1, and that means one head showing. That can be HTT or THT or TTH. That's it, right? Okay, 2. Random variable will be 2 for the outcomes of HHT, HTH, THH. Did I miss anything? No, right? That's it.
No.
All right. 3. Which outcome will give you 3?
Head, head, head.
Right.
Yeah.
Okay. There's only one outcome will give you 3. Okay. So frequency. Frequency here is for the first one.
1,
1,
For the second one,
3,
3,
3. Third one,
3,
and 1.
1.
So probability distribution, if they ask for probability distribution, we can do that. The sum, you can add up the frequencies 6, 7, 8, right? Which is same as the count of all the elements in this third column. So what is the probability for x equal to 0?
1/8.
1/8. Y equal to 0, x equal to 1,
3/8.
3/8. X equal to 2,
3/8.
x equal to 3 is,
1/8.
and if I add them up, I should get,
1.
okay. So now we have everything written down. We can answer the question. The range of values, the range of x is, anybody?
0, 1, 2, 3.
Right, 0, 1, 2, 3. Those are the values x takes. So we have that. Right. Okay, now classify. What's the classification?
Finite discrete.
Finite discrete. Okay, so part A is done. Part B is on the board. We have all of the numbers worked out on the board. So that problem is all done. So what I have shown in the on the board, except the third column. In the third column, I showed the actual outcomes. You don't need to show that. You only need to show the first column, second column, and the fourth column to answer this question. But if you show the details like I did, then it'll be easier for you to work out the numbers. Okay, now the histogram. We need to understand histogram. A histogram is a way of showing these numbers in a picture. And for anybody seeing a picture, they say a picture is worth 1,000 words, which is true. Showing a picture is always very revealing, a lot more revealing than looking at the numbers, because you can see the pattern of how they behave. And so showing these numbers in a picture is always the best way to demonstrate. And you have seen all the business people in the business, when they have to demonstrate things in the meeting and show how their business is behaving, they always use these histograms to show how things are going. So you need to learn how to do that. So here are the values. So to draw the histogram means you have to have the frequencies. Sometimes they will ask for histogram of the frequencies. Sometimes they'll ask for histogram of probability. But for any problem, both histogram of frequency and histogram of probability will be identical. They will not be different. But you have to show the numbers that they are asking for. So here is how you show histogram of frequencies. You make you list your values of the random variable y are 2, 3, 4, 5, 6, 7, 8. So you have to find those numbers. You had to put those numbers on the x-axis. So you can cover two rectangles in the graph paper. See, I'm doing two rectangle space for the number one, number two, another two rectangle space for number three. I'm choosing that to make the picture wide enough. And then number four occupies two squares on the graph paper. And so in that way, I plot all the values of the random variable on the x-axis. Always value of the random variable goes on the x-axis. And on the y-axis, these numbers, you see 1, 2, 3, 4 on the y-axis, they represent the frequencies in this case. And value of random variable 2 has frequency 1, so I have a bar of height 1. And value of random variable y has a frequency of 2, so I have a bar of height 2 to represent that. So you draw bars of height equal to frequency everywhere. And then at 5, we have the highest, the tallest bar. And then 6, 7, 8 are 6, 7, 8 are lower. See, when I look at these numbers in this table, you know, it's not very revealing, but when I look at this picture, I can see that number 5 has the highest frequency. Number 2 and 8 have the lowest frequency. See, all those are right visible. And the whole pattern is as the numbers go up, the frequencies go up and then down. See that? It goes up and down. All that pattern can be seen in the picture. Now, when I show the histogram of probabilities, only difference is in the y-axis, I show 1 over 16, 2 over 16, 3 over 16, and so on. See, I have these numbers unreduced. Don't reduce them in your probability distribution. See, 4 over 16 is equal to 1 over 4, right? I didn't do that because only if you keep them unreduced, it's easy to put them on the histogram. 1 over 16 is right here, first two boxes are used to represent 1 over 16. The next two boxes, 2 over 16, 3 over 16, and so on. So instead of 1, 2, 3, 4, you have 1 over 16, 2 over 16, and so on. That's the only difference. But still, the bars are of the same height. Okay, so these from these bars, from these histograms, you can tell the pattern. The bars are going up and down. The heights are rising as you go to from left to right. They're rising and then falling. This pattern is called normal. Why is it normal? This is how a normal data behaves. If you take data from real life, for example, let's say I'm analyzing number of people. To give you a simple example, we don't normally analyze this kind of data, but you're analyzing data, which represents number of people in different cars in a train. Do you agree that the number of people or frequency represents number of people in the middle car? Do you agree that the middle car will have the highest frequency and the end cars have the lowest frequency, right? Normally, isn't that normal, right? So that's why. Normal behavior of data is always the ending values have lower frequency and middle values have highest frequency. Here's another example. In the last exam in Mat108, how many students had low scores, like 30s and 40s? Small number. How many students had 95 and 94 and 92? Small number. How many had grades in the range 60s and 70s? Largest number, right? That's how it's always happened. That's normal. So the frequencies at the ends will be lower, frequency in the middle will be higher. That's when we call that the data is behaving normally. And the histogram that I have here is called normal histogram. The data is behaving normally. All right, so we need to stop here. We are out of time. I just explained normal distribution. So I will have questions on the homework up until that point, normal distribution. All right, yep, everybody enjoy the rest of the day. I'll see you Monday. Have a nice weekend, everybody.